Hey girls, yesterday we left off on solving quadratic equations by graphing, and we were looking for the x-intercepts of the graph, or in other words, where the graph crosses the x-axis to find the solutions to the equation. And we left off on this problem where the graph, that parabola here, didn't cross the x-axis at all, so our final answer was that there was no real solution for that equation. We said you can't just put no solution because what we're learning later in the chapter is that it actually does have solutions. They're just called imaginary solutions. There's no real solution, but there are two imaginary solutions for that quadratic equation. So today we're going to learn about imaginary numbers. So scroll down into Goal 4. First, we're just going to learn about pure imaginary numbers and how to just do operations with them, meaning like adding, subtracting, multiplying, and dividing them. So you have to know what the imaginary number is. I is the imaginary unit, and it's defined as I equals the square root of -1. In the past, we always said that if you do the square root of a negative, it's going to give you an error on your calculator, and you just can't do that. But you can, as long as you're working in imaginary numbers. So if you are looking at a pure imaginary number, it means that there's pretty much like an I in it, but there's no real number part of it. So for example, like it could be an I multiplied by a whole number like 6. It could be an I multiplied by an integer like -2, or it could even be an I multiplied by a radical like square root of 3, but it's not going to have like 6i plus 2 or something like that. That's something else different called a complex number, where it has a real number part and an imaginary number part. For now, we're just going to keep it simple. It's just one term, 6i, or just -2i, or just I square root of 3. In order to simplify imaginary numbers, you'll want to know some things about the powers of imaginary numbers. So let's start out by drawing this little circle, because this will help us remember our powers of the imaginary number. I to the first power, we just said, is equal to the square root of -1. But if you have I to the first power, you're just going to leave it as I. You don't want to change that to the square root of -1. You're just going to leave it as I, but in your head, you know that it's equal to the square root of -1. Now, when you see something like I squared, you do have to simplify that. The reason why is because I squared is the same thing as square root of -1 times the square root of -1, or in other words, the square root of -1 squared. If we know I is the square root of -1, then when we square that, the square root and the squared cancel each other out. So I squared can simplify down to just -1. Next on our circle here, we have I cubed. If we break apart I cubed, we could treat that as I squared times I. We just said that I squared can be simplified to -1. So this is like saying -1 times I. If you multiply -1 times I, you get -I. So if you have I to the power of 3, you're going to simplify that to -I. Lastly, we go I to the power of 4. We can split that apart based on our power rules. We know that that can be split apart to say I squared times I squared. We already know I squared is equal to -1, so that's like saying -1 times -1. I'm going to use parentheses here just so it doesn't look like it's subtracting. We know that when we take a negative times a negative, we get a positive. So -1 times -1 gets us +1. I to the 4th can be simplified to +1. After that, it starts to repeat. Because think about it, if you have I to the 5th, you could break that apart to be I to the 4th times I. But we know I to the 4th is just 1. So you have 1 times I, that's just I. So after that, it's going to just start to repeat. I to the 6th is going to be the same as I squared. I to the 7th would be the same as I cubed. I to the 8th would be the same as I to the 4th. I to the 9th would be the same as I to the 1st, and so on. You get the point here. It will just start going on and on around the circle. Let's say you wanted to simplify I to the power of 50. Instead of sitting here and going, okay, this is I to the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and counting all the way up to 50, what you can do instead is take whatever the power is on I and divide it by 4. You will always divide it by 4 since there's 4 steps around this circle chart. Okay, we have to remember our long division here. So let's think. First, we look at the highest digit spot. Right now we have the tens place. How many times can 4 go into 5? It can go in 1 time. So that goes right above the 5. You divide, then you multiply. 1 times 4 gets you 4. Then you subtract 5 minus 4 gets you 1. And you bring down the next place. Remember, the steps are divide, multiply, subtract, bring down. So we divide 10 by 4 gets us 2, multiply 2 by 4 gets us 8, subtract gets 2, but there's nothing left to bring down. At this point, you repeat or remainder. So if you wanted to repeat, you could add decimals, or we say, okay, this is a remainder of 2. What this means, since you got 12 remainder 2, is that you're going to go all the way around the circle 12 times with a remainder of 2 steps. Whatever the remainder is, that's going to tell you what the power of I is that it's equal to. So if it's a remainder of 2 steps, that means that I to the 50th is the same thing as I squared, since it was a remainder of 2. Let's go ahead and put those remainders around the circle. So I went ahead and filled in. If you have a remainder of 1, it's the same as I to the first. Remainder of 2 is I squared. Remainder of 3 is I cubed. But you're never going to have a remainder of 4. If you're dividing by 4, that would be no remainder at all. So this is a remainder of 0. Now let's think of this in decimal form in case you did have your calculator or you did divide it out with a decimal. If you have a remainder of 1, that's as a fraction 1 out of 4, which would be equal to 0.25. So if you have any whole number with a 0.25 decimal, that's going to be the same as I to the first. A remainder of 2 would be the same as 2 out of 4 as a fraction, or 0.5, a half, as a decimal. So if you divide your number and you get a 0.5 decimal, you know that you're looking at I squared. A remainder of 3 would be the same as 3 out of 4, which as a decimal would be 0.75. So if you divide your power by 4 and you get something with a 0.75 decimal, you know you are equivalent to I cubed. And a remainder of 0 would mean that there is no decimal. It's just a whole number answer. So coming back to our problem, since we know I to the 50th is the same as I squared, then we'll say to simplify I to the 50th, you would get negative 1, because I squared is equal to negative 1. I wouldn't suggest memorizing all of this full circle. What I would suggest memorizing is that I is equal to square root of negative 1. So then think about how you can break it down. You break it down into the square root of negative 1 squared, I squared times I squared times I squared. That way you don't have to memorize I, negative 1, negative I, 1. Instead, you're really understanding where these numbers are coming from so that you can figure them out. But to review, let's make sure we all understand what it is we would put when we're simplifying. I stays as I. You don't change that to the square root of negative 1. However, I squared, you always change to negative 1. I cubed, you always change to negative I. And I to the 4th, you always change to positive 1. After that, it keeps repeating around the circle like we talked about. Alright, let's try some examples with square roots of negative numbers so we can really see where I comes into play. If you were trying to simplify the square root of negative 27, you'll know that there's going to be an I in the answer, because anytime you see a negative under a root, the answer is going to have an imaginary number. So just like what you would have done in Algebra 1 when you were breaking down the simplifying a square root, you're going to start with a factor tree. Anytime it's a negative, you always want to make -1 and the number the first 2 steps on the factor tree. Now, this way, you can just focus on 27. What are the factors of 27? 2 doesn't go into it because it's not even, but 3 does go into it. I know that 3 goes into 27 because a nice trick for 3s is that if the digits 2 plus 7 add up to 9, if those digits add up to something that's divisible by 3, then that means the number itself is divisible by 3. That only works for 3s, but in this case, since I know 9 is divisible by 3, I know 27 is also divisible by 3. 27 divided by 3 makes 9, and then 9 is not a prime number. It can also break down into 3 times 3. You have to break it all the way down into prime numbers. Once you get to the prime numbers, now you're going to look for any matching factors. The factors don't have to be next to each other on the factor tree. So like, for example, these 2 3s I can treat as a pair. And then I still see I have a -1 and a leftover 3 here. I'm going to split up each of these into their own square root. However, when I see a pair like this 3 times 3, instead of writing those as 2 separate 3s, I'm going to write it as 3 squared. And then I have my leftover 3 by itself. The reason why I'm going to put that as 3 squared instead of 3 times 3 is because I know a square root and a squared can cancel each other out. Besides just canceling out the square root and squared, you always change the square root of -1 to an I. So I have I, and then 3, and then square root of 3. Since that blue 3 didn't have a pair to go with it, it has to stay under the root. It doesn't have a squared to be able to cancel out the square root, so it has to stay under the square root. It can't come out. Now, once you're here, you have I, 3, square root 3. You just have to rearrange this. They're all technically multiplied by each other, and we know the order of multiplying doesn't matter. But when you write your final answer, it should be in the order with the number first, then the I, and if you have a square root, that comes at the end. So your final answer here should be 3i square root 3. Let's try another one, like square root of -216. Like I said before, split off the negative first. Now, since this is even, I know it can divide by 2. 216 divided by 2 makes 108. That's another even number, so I can go ahead and divide by 2 again. I get 54. That's another even number. I can go 2 and 27. Now, you might remember from before, 27 broke down into 3 times 3 times 3. So I'm going to go ahead and make those 27 into 3 branches, 3 times 3 times 3. Now I look for factor pairs. I see a pair of 2s. I see a pair of 3s. And then I have my leftover -1, a leftover 2, and a leftover 3. I color-coded these. Anything with a pair, like this 2, gets written as 2 squared so that it can cancel out the square root. Same thing goes for this pair of 3s. You write it as 3 squared so it can cancel out the square root. Remember, the square root of -1 makes an I. So right now I have I, and then 2, and then 3, and then square root of 2, and square root of 3. Right now, as it's written, it looks like 23. Remember, like we said before, these are technically all multiplied together, so you need to either put a multiplication symbol there or a parentheses, something to show it's not 23, it's 2 times 3. These are all multiplied together. Now rearrange it. So 2 times 3, that makes 6, so the 6 comes first, then the I, the root comes last. You have to multiply these back together, 2 times 3, to make 6. So your final answer is 6i square root 6. Go ahead and try the practice problems below. Here are the final answers for those two.